Significant events in time and space tend to leave lasting fingerprints on the universe. It's safe to say that the Big Bang, the cataclysmic event that occurred 14 billion years ago and gave origin to our universe, has left an indelible mark on everything we see today. The cosmic microwave background, CMB, the primordial microwave radiation that permeates the universe, is the most permanent of marks left by the event. For the first few 100,000 years, our newborn universe was a teeming, hot, dense plasma made up of nuclei, electrons, and photons for the first few 100,000 years. The universe had expanded and cooled to below 3,000 Kelvin by the time it was 380,000 years old, allowing neutral elements, including atomic hydrogen, to form. Due to the lack of free electrons, light finally flooded the cosmos, and the CMB emerged. Thus, this relic radiation represents a flawless record of our universe in its infancy. Due to the universe's expansion, the CMB has been stretched to its current microwave wavelength and cooled to a temperature of just 2.7 Kelvin. The CMB has provided the scientific community with lots of data since it was initially predicted in the late 1940s, and then experimentally detected in 1964. However, it's revealed some puzzling mysteries and anomalies, such as a substantial disparity in the CMB detected in the two hemispheres of the sky. The fascinating enigma is a huge, exceptionally cold area on the CMB that spans over 1 billion light-years. The so-called CMB cold spot, which was first discovered in 2004 by NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed by the European Space Agency's Planck satellite, is about 70 microkelvins colder than the average CMB temperature and appears in the southern celestial hemisphere. While it's possible that the cold spot arose from the same primordial density fluctuations that formed the CMB's temperature anisotropies, this isn't very certain. These anisotropies have a Gaussian distribution, which allows for minor but not huge fluctuations on the scale of 18 microkelvins. However, the cold spot is nearly 150 microkelvins colder in certain regions than the mean CMB temperature, well above what a Gaussian distribution would predict. Furthermore, the radius of the cold spot is around 5 degrees, although the most significant temperature changes in the primordial CMB occur on angular scales of about 1 degree, making it even more bizarre. It should come as no surprise then that scientists worldwide have proposed a variety of theories about the CMB cold spot, and numerous investigations are being conducted to learn more about its origins. Some early theories suggested that the cold spot could represent foreground contamination from within the Milky Way in the form of galactic dust and synchrotron radiation, or the result of strange celestial objects. However, the NRAO VLA Sky Survey, NVSS, the 2-micron All-Sky Survey, 2MASS, and the Sloan Digital Sky Survey, SDSS, as well as detailed Hubble Space Telescope photos, all revealed no such objects. One good explanation for the phenomenon is that there is a vast cosmic supervoid between us and the cold spot because of the large-scale structure of the cosmos. While galaxies can still be found within voids, their matter density is substantially lower, 1/10 of the average, than in other parts of the universe. On the other hand, the universe has superclusters, large regions with considerably more galaxies than the average. Another explanation for the CMB cold spot could be the peculiar motion of galaxies in the region due to severe gravity effects. This could be similar to the effects seen in the Great Attractor, an apparent gravitational anomaly at the center of the local Laniakea supercluster caused by an enormous concentration of mass, and the related dipole repeller, a center of effective gravitational repulsion in the large-scale flow of galaxies in our local group, caused by the likely presence of a supervoid. Both have left their impressions on the CMB dipole, although no such strange structures have been seen in the CMB cold spot area or the surrounding regions. Perhaps the answer to the CMB cold spot might be found inside rather than outside the notion of inflation. It's possible that a local patch of the universe had a longer period of inflation during the inflationary epoch in our universe's infancy, resulting in the formation of a cold spot in that region. Improved understanding of cosmological factors will allow scientists to better explain unusual phenomena such as the cold spot. New data from highly sensitive telescopes like the Meerkat Array and forthcoming facilities like the Giant Magellan Telescope and the Square Kilometer Array are required for this. The current understanding of the CMB cold spot does not allow scientists to draw any definitive conclusions. To fully comprehend it, they must either improve their observations or revise their view of the universe. Future observations from more advanced ground and space-based observatories should hopefully lead to a better understanding of this perplexing scientific phenomenon. If you like this video, please consider subscribing and click the notification bell so you do not miss any upcoming videos.